second talk of today is given by Muthusamy Rajaguru. And yes, the title is Moduli stabilization in type 2B models with H11 equals to 0. So please, the stage is yours.
So I'd like to begin by thanking the organizers for this opportunity and for keeping the seminar series running. So today my title will be Moduli stabilization in type 2B models with H11 equals 0. This is ongoing work with my amazing collaborators, Katrin, Eduardo, Anindya, Johannes, and Tim. So this is the brief outline for my talk. I will begin with a very broad motivation and then review some of the aspects of these non-geometric models that we'll be working with, and then discuss moduli stabilization in these models in the context of the swampland and conclude. Okay. So as this audience already knows, the swampland program is an effort to classify effective field theories based on whether they have UV completions to quantum gravity. And a happy byproduct of this swampland program has been added scrutiny on existing string constructions. This has enabled us to sharpen the boundary between the landscape and the swampland. And one other aspect that we would like to focus on in this talk is to expand the string landscape in order to better help the swampland program. I'd also like to mention that the expanding the string landscape is an interesting problem in its own right. The tools that we'd like to use for expanding the string landscape is these non-geometric models, which have already proven to be pretty novel testing grounds for various conjectures. For example, in March last year, among many other things, we studied the ADS distance conjecture in these settings. And more recently this year, we attacked the very interesting question of finding asymptotic accelerated expansion in non-geometric models. But I'd like to point out that in both these papers, we didn't find major departures from the intuitions of geometric constructions. The reason for this is presumably that we restricted to just what would be the bulk moduli in the mirror setting and studied large complex structure limits of these bulk moduli. And so this seems to suggest that if we want to capture any new physics and provide more non-trivial tests for swampland conjectures, that we'd like to actually move away from this large complex structure limit and study the full Landau-Ginzburg model that we're interested in. And some efforts towards this were made by my great collaborators last year in the context of studying the tadpole conjecture. In my talk today, I'll speak about work that is trying to further this program. So the feature in specific that we would like to test is moduli stabilization, which of course is an extremely important problem for string phenomenology. But the motivation for studying moduli stabilization in this talk will not come from phenomenology, but instead will come from the swampland program, and in specific, the tadpole conjecture, which was already mentioned in the previous talk. So in specific, I'll restrict to the type 2B version of the tadpole conjecture, which is what will be relevant for our discussion here. And the rough statement is that the fluxes that are used to stabilize the moduli contribute to the tadpole via this constraint. And there have been several authors who worked on this. I've tried to list them here, and I apologize if I missed anyone. And as we saw in the previous talk, there have been various refinements of this conjecture. And in specific, this conjecture has been studied very extensively in the asymptotic limits of moduli space, which is where we seem to have sufficient control to make sharp statements. But it's a very interesting question to ask, just like any other swampland conjecture, if it holds in the interior of the moduli space as well. And this is sort of the question that we'd like to pose using non-geometric settings. And there's an even further interesting question, I would say, that even if it does continue to hold, can we still find models where all moduli can be stabilized? Essentially, in the context of this talk, the question that I'll be asking is, can we find fully stabilized n equals 1 supersymmetric Minkowski vacua? So having motivated what we're trying to do briefly, let me move on to review the setup that we're going to use. So DJKT showed that it's possible to stabilize all moduli in type 2A compactifications on a rigid Calabi-Yau using just geometric fluxes. And motivated by these results in type 2A, Becker, Wafa, and Walcher tried to construct the mirror dual of this in type 2B. Now, naively, you would think that a rigid Calabi-Yau does not have a well-defined mirror dual, but thankfully we have a Landau-Ginzburg description, which we can use. And in particular, the two Landau-Ginzburg descriptions that we will use are actually Gepner models, just the 1 to the 9 Gepner model and the 2 to the 6 Gepner model, which were worked out by Becker, Waffa, and Walcher. So these models have no Kähler moduli, and this naively seems like this provides a way out of the problem of volume stabilization in type 2b. But the story is a bit more complicated, and discussing non-supersymmetric vacua is quite hard in these settings. And also, I'd like to point out that this, whilst it sounds very similar to Giddings-Kachuru-Polchinski, has some subtle differences. For example, this is the Kähler potential. I've just highlighted the Kähler moduli dependence and the axiodilaton dependence of the Kähler potential of GKP. And the supersymmetric equations then give us ISD fluxes. Whereas the Kähler potential in Becker-Waffa-Walcher's constructions looks different. In specific, it gets this factor of 4 in front of the axiodilaton, and there are no Kähler moduli deformations. This can be argued for using mirror symmetry from the type 2a DJKT construction. And as a result of this, the supersymmetry equations do not require ISD fluxes, unlike in GKP. But for the purpose of this talk, I will be restricting to supersymmetric Minkowski solutions. And for these purposes, GKP and Becker-Waffa-Walcher are almost identical, except for the absence of Kähler moduli. And so asking for W equals 0 vacua, we find that we need a flux of this nature. But before discussing flux vacua, I need to first discuss the flux superpotential in these non-geometric settings. And the original derivation of the Gukov-Waffa-Witten superpotential doesn't actually rely on the existence of a geometric manifold. It was derived and argued for on general grounds using CFT techniques. And so these continue to exist in these type 2b models as well. And what is very non-trivial is that the superpotential is argued to be completely exact. And this will be very important for what we will do, because we will be at strong coupling and small complex structure. And what I'd like to introduce you to now is the non-geometric counterparts to all the ingredients that go into computing the Gukov-Waffa-Witten superpotential. So just to be concrete, let me look at the 1 to the 9 model first. And in specific, I will break it down into its minimal model building blocks. So I'll just focus on the single variable building block of the 1 to the 9 model, which we mod out by this discrete symmetry. X here is a chiral superfield, so it's a complex field. In order to find what a homology basis is for this associated manifold, we can lift this literature straight from the result. We look for directions in which, in the X plane, in which the imaginary part of this worldsheet superpotential vanishes. And there are 3 such cycles which are related by this constraining equation. And the cohomology basis is given in terms of the Ramon-Ramon ground states of the minimal model. For this single variable superpotential X cube, there are 2 Ramon-Ramon ground states. And these can be equivalently represented in terms of the elements of the chiral ring, because they're isomorphic. And having described both the cohomology and the homology basis, we can then readily calculate the overlap integral between these cycles and the RR ground states, which is given here in this expression. At this moment, I'd like to point out that there is also a corresponding Poincare dual cohomology basis associated to this, to these cycles that we described here. And this will be relevant later when we actually discuss how one goes about finding W equals 0 vacua. And the 1 to the 9 model has the following Hodge numbers. It has no Kähler moduli deformations and 84 complex structure moduli. And the full worldsheet superpotential for the 1 to the 9 model is shown here, which is made up of these 9 minimal models. And generalizing readily from what I discussed in the single variable case, the RR ground states can be labeled by a set of 9 integers, where each integer takes a value 1 or 2. And in specific, we're interested in elements of H2, 1 and H3, 0. So there is one H3, 0 form. Sorry, there's one holomorphic 3, 0 form. And we have 84 of these. But we would actually like to restrict to a specific orientifold of these Gepner models. There are many orientifolds that have been worked out by Becker and collaborators. But we will restrict to the one which has the highest charge, so that it gives us the highest tadpole and the potential to possibly test the tadpole conjecture. So in particular here, this orientifold leads to a charge of 12, which needs to be cancelled by our fluxes. Similarly, the other model that we're interested in is the 2 to the 6 Gepner model, where the single variable building block potential is this x to the 4 potential shown here. And just like in the 1 to the 9 model, a cohomology basis is given by the RR ground states. Here, the labeling goes over L equals 1, 2, and 3. And there are 4 cycles which obey these constraint equations. And just as before, we can compute the overlap integral. And this readily generalizes to the full model, where in this case, we have 90 complex structure moduli and no Kähler moduli. The important thing here, the takeaway here, is that the orientifold that we will work with has an orientifold charge of 40 that has to be cancelled by fluxes. And this will become important later in my talk. Okay, so just to give you a brief executive summary of what we're trying to attack here. So after the orientifold in the 1 to the 9 model, we have 64 moduli, including the axial dilaton. And the target from the tadpole conjecture is that we'd like to stabilize 36 or more moduli. And similarly, for the 2 to the 6 orientifold that we picked, there are 91 moduli, including the dilaton. And here, interestingly, the tadpole conjecture would not imply that we cannot stabilize all these moduli. So I will come back to this towards the end of my talk, but this non-geometric model gives us a potential where even if the tadpole conjecture continues to hold in the interior of the moduli space, we would still be able to stabilize all of the moduli. Okay, so having set the target, now let me actually describe the scheme that we are using and how we hope to stabilize this moduli, or how we are stabilizing these moduli. Okay, so what goes into actually constructing a supersymmetric Minkowski vacua? So the first step is to pick fluxes from H2, 1, but we are not done there because we need to ensure that these fluxes are quantized. And how we guarantee this is by going to the Poincare dual basis to the cycles that I showed before. And the integral basis is comprised of these Poincare dual forms. And we also need to ensure tadpole cancellation. So this is already a very non-trivial problem. And what we find, and there are many such solutions which are known already from 2006 from the work of Becker, Waffa, and Walcher. But what we find is that all these solutions generically have massless directions. For example, last year, a thorough scan was done of these solutions for W equals 0 vacua, and the maximal mass matrix rank that was found was 26. So this is out of 64 moduli, only 26 are massive. But this is not the end of the story, because in principle, we could use higher order terms in the superpotential to stabilize these massless moduli that are left over. And for this, what we essentially do is use the fact that we can compute derivatives of the superpotential at the critical points. I will flash the derivative formula in a moment, but first let me finish describing the scheme that we're using. So the idea is to expand the superpotential around these critical points, where the linear term and the constant term are vanishing because these are supersymmetric Minkowski critical points. And the T's are the complex deformations away from the critical point. And we would like to ask if order by order solving for critical points in this expansion would give rise to flat directions being lifted. So for example, taking the expansion up to quadratic order and then solving the critical point equation would give us linear constraints, which would tell us what the massive fields are. And this is always consistent, of course, with the mass matrix rank. And then subsequently, more non-trivial constraints can arise. For example, from the cubic terms, quadratic constraints, from the quartic terms, cubic constraints, and so on and so forth. And after having already plugged in the fixed fields, if we are able to fix any other of the massless fields, then we say that they are stabilized or fixed. And we're able to perform this because of these Landau-Ginzburg techniques that allow us to compute derivatives. So for a single flux choice in the superpotential, we'd be able to compute exactly what the rth derivative with respect to the complex deformation is. And so in principle, this gives us arbitrary power to compute this expansion up to higher order. But of course, in practice, we are limited by computational capabilities. For now, we've reached 7th order in the expansion for the 1 to the 9 model. One point I'd like to point out also here is that while computing these derivatives can be done numerically and hence sped up and so on, solving the polynomial constraints cannot be done numerically because your usual optimization codes could potentially fix more fields than need to actually be fixed by specific constraints. We need to use analytic techniques for this. And so furthering this computation to higher and higher order doesn't necessarily give us complete control. It's solving the polynomial constraints where the actual bottleneck is. But let me illustrate all this with an explicit example. So here is a flux choice, which gives a supersymmetric Minkowski vacuum. The mass matrix rank for the solution is 16. And the already massive fields can be fixed order by order with no ambiguity. As you expand higher and higher order in the superpotential, you can keep solving the higher and higher order constraints you get for them, and they get fixed unambiguously. Now, turning towards the fields that we're actually interested in, the massless fields. For example, consider some field T20, which is massless, which could get fixed potentially from the cubic terms for the massless fields. For this specific example, there are 6 new stabilized directions which arise when you actually look at the cubic order terms. But I'm focusing on this, let's say, one specific field that gets fixed in this analysis. Unlike the massive case, the massless fields can lead to several branches of solutions because different orders that arise in this expansion need not get fixed at the corresponding constraint order. For example, the quadratic piece that comes from this massless field can get fixed when you're only at the 6th order in the superpotential, not necessarily at cubic order. And this provides a very non-trivial problem. It is very hard to automate this problem of finding stabilized fields. We actually have to do this meticulously one by one, and at least to several branches which merge and diverge at different points in this expansion. However, we are still able to make significant progress towards analyzing the wide range of solutions. One very important step in this has been classifying the various solutions that one can get. And this has been done recently by Katrin, Anindya, and Nathan Brady in a very nice paper from last month. And using this kind of classifications and the constraints that we get from the tadpole, we are moving towards analyzing general patterns and using symmetry arguments of these Gepner models to show that perhaps generically what is and what not, what is possible and what isn't. So let me just flash a snapshot of the results that we have so far. So the first column here labels different solutions. Even though this looks like a small list, a lot of these solutions are related to many more solutions by symmetry operations. And hence, this is actually already a fairly extensive search. It's not completely exhaustive, but it's fairly extensive. And one pattern that you'll notice is that the number of fields that get fixed at higher and higher order seems to die off. So for example, we start with this branch with 16. It seems like we get to 24, and then to 26, and then it just dies off. And the bound that I pointed out for the 1 to the 9 model was 36, if you remember. And as you can see, nothing here gets even close to 36. And so you might think, okay, the tadpole conjecture is safe, and here's a non-trivial test. But then again, at the 7th power in the superpotential, there are non-trivial constraints that start arising. Actually, using these constraints to fix Moduli has been very, very difficult, and we haven't managed to achieve this so far. But this seems to suggest that at later powers in the expansion, we can pick up non-trivial terms, and it's not guaranteed that we will not hit this bound of 36. But we are still quite far away, and doing this in a reasonable way still seems quite far away to us, at least. Okay. Now let me move on to the 2 to the 6 model, where things look slightly more promising and interesting. So the 2 to the 6 orientifold, as I pointed out, has a tadpole charge of 40. And here we already have solutions with a maximal mass matrix rank of 82 over to the 91 moduli. So we only need to lift 9 of the massless moduli to potentially stabilize all of them, and this would still be compatible with the tadpole conjecture. One thing we do find so far is that the results from this model have remained consistent with the massless Minkowski conjecture, which suggests that you can't find Minkowski vacua with all fields massive. And also, I'd like to point out that the higher order stabilization here, even though it looks much more in touch with, much more within touching reach, is highly complicated. And just to give you a flavor for the kinds of solutions we're dealing with, this is a flux choice that leads to 82 massive fields, for example. Naively looking at this, you would think there are contributions from various fluxes. You should be able to lift fields at higher order. But unfortunately, in practice, these are all related by symmetry operations, and a lot of the higher order contributions cancel in a very intricate way to make sure that we aren't able to lift as many fields as we would like. But progress in this is still very preliminary. In the root of the 6 model, we are still classifying the types of solutions that we have with respect to the tadpole contributions that they have. And in the coming weeks, we hope to have more concrete results and hopefully make progress towards finding perhaps the first fully stabilized n equals 1 supersymmetric Minkowski vacua. So I'm just about on time, I hope. So I'd like to finish with my brief summary. So I hope I've convinced you that non-geometric Gepner models are promising tools for the swampland program, and that moduli stabilization is indeed possible with higher order terms in the superpotential. Whether or not this breaches the tadpole conjecture is not completely clear, although to the best of our knowledge, it seems the tadpole conjecture still appears to hold even in the interiors of moduli space in these non-geometric models. And stay tuned for our results very soon. Thank you.
Thanks a lot, Muthu, for the nice talk. So now we have some time for questions. No question? No question from Muthu? Okay. So we have one from Jose.
Yeah, it's a very, very nice question. But yeah, first of all, thanks for the talk. Very nice talk. I was wondering because the idea here is that if you include higher powers of the derivative of the potential, you can find that actually there is not a flat direction, but the modulus is stabilized, right? But still, it's not like it's massive, right? So do you think that helps to avoid constraint on feed forces and all that, or that wouldn't help for this?
I think that, yeah, that's a very nice question. To the best of my understanding, it doesn't help with this. So for phenomenology, that's why I said that this is not really motivated directly from studying phenomenology. This is more just to understand the tadpole conjecture. I still think there would be these long range forces, and this wouldn't solve that problem.
Okay, thank you.
Okay. Do we have more questions? Okay, if not, I would like to thank Muthu and Jeroen again